Module 3, Lecture A, Engineering Functions. By the end of this lecture, you will be able to define functions that perform focused engineering calculations with clear parameters, return calculated results without mixing computation and user-facing output unnecessarily, and document assumptions, units, and expected inputs using concise docstrings and comments. Function design. Defining function purpose. Define a function by the single engineering calculation it performs, such as finding pressure drop, beam load, or heat loss. A clear, focused purpose makes the function easier to name, test, and reuse. Avoid mixing the calculation with unrelated work, like user input or report generation. A well-designed function should have a clear, simple purpose, focused on one specific task, such as calculating or estimating a value. Keeping functions narrow separates the main engineering logic from unnecessary software complexity. Functions that try to handle too many concerns become harder to check, reuse, and integrate, while concise functions are more predictable and adaptable. In engineering software, each function should have a clear, narrow purpose, such as calculating the Reynolds number from the needed fluid mechanics quantities. Related tasks, like deciding whether flow is laminar or turbulent, should be handled by separate functions. This modular design makes the code easier to test, adapt, and trust as part of a larger analysis. Python code. Defining function purpose. Design each function to handle one engineering calculation, and keep the calculation logic separate from anything shown to the user. Before implementing, clearly document the units being used and any assumptions behind the work. The required area function calculates the area needed for a given load and allowable stress. Before doing the calculation, it checks that the load is positive. If the load is 0 or negative, it raises an error to prevent invalid input. The function first confirms that the allowable stress is positive and raises an error if it is not. It then finds the required area by dividing the load by the allowable stress, giving the area needed to support the load safely. The function returns this calculated area. The format area report function takes an area in square meters, converts it to square millimeters by multiplying by 1 million, and returns a readable report value. The result is rounded to 1 decimal place and labeled as millimeters squared, making the output clear and user-friendly while keeping presentation separate from the calculation. The applied load is set to 12,000 newtons, representing the force the material must carry. The allowable stress is 150 million pascals, which is the maximum stress the material can safely withstand. Together, these values are used to determine the required area so the material supports the load without exceeding its stress limit. The required area is calculated by calling a function with the applied load in newtons and the allowable stress in pascals. The function returns the safe area needed in square meters, so the load does not exceed the stress limit. Keeping this calculation separate from the output makes the process clearer and reusable. The example separates output formatting from calculation logic to keep the code modular and easier to maintain. A formatting function takes the calculated area, converts it from square meters to square millimeters, and returns a clear summary string. The program then prints a short label for format function usage, followed by the formatted area report. The required area is recalculated using a load of 18,000 newtons and the same allowable stress as before. The new result is then passed to the area report formatting function, which converts it from square meters to square millimeters. Finally, the The formatted message is printed to clearly report the required area. The script calculates the required area from a load and an allowable stress, after confirming both values are positive. It divides the load by the stress to get the area in square meters, then converts the result to square millimeters for easier reading. It prints the formatted result and repeats the calculation with another load, showing that the calculation and output formatting are kept separate for clarity and reuse. Parameter planning. Parameter planning means deciding exactly what information a function needs to perform an engineering calculation correctly. A good function clearly names its inputs and avoids hidden assumptions. So quantities like length, pressure, or other relevant values are explicit. This makes the function a reliable tool that uses known inputs, carries out a defined calculation, and returns trustworthy results. Choose parameter names and groupings that clearly show what each input represents, including the expected unit when helpful. A function should take only the information needed for its calculation, such as engineering quantities like flow rate or efficiency. Avoid adding unnecessary parameters because they make the function harder to test, easier to misuse, and less focused. When choosing function parameters, balance convenience with clarity. Defaults can simplify use, but they may hide assumptions that fail in different settings, so critical values should be provided explicitly. Well-documented stable defaults and direct control over inputs make functions easier to verify, more transparent, and more reusable. Python code, parameter planning. Before writing engineering functions, plan the parameters they need. Name inputs clearly using the physical quantities and units they represent, and have functions return results rather than printing them internally. The hydraulic power in kilowatts function calculates the pump power needed from a flow rate, pressure rise, and efficiency. It assumes standard international units and uses an efficiency of 1 when no value is provided. This makes the pump power calculation clear, reusable, and focused. The code checks that both flow rate and pressure rise are non-negative before doing the hydraulic power calculation. If either value is negative, it raises an error because negative flow or pressure is not physically meaningful in this context. The code validates that the efficiency value is realistic by requiring it to be greater than 0 and no more than 1. If the value is outside this range, it raises an error explaining the requirement. This prevents invalid efficiency inputs from causing incorrect pump power calculations. The function estimates the pump power needed by using the flow rate, pressure rise, and efficiency to calculate hydraulic power. It then converts the result from watts to kilowatts and returns the required pump power. To calculate the pump's required hydraulic power, we define 3 key inputs: a flow rate of 0.035 cubic meters per second, a pressure rise of 180,000 pascals, and an efficiency of 0.72. Together, these describe how much fluid the pump moves, how much pressure it must add, and how effectively it converts input energy into useful work. The hydraulic power kilowatts function is called with named arguments for clarity. It uses the flow rate, pressure rise, and pump efficiency to calculate the required shaft power in kilowatts, then stores the result as power kilowatts. This output presents a concise parameter planning summary for a pump calculation. It reports the flow rate in cubic meters per second, the pressure rise in pascals, and the pump efficiency as a decimal. It then shows the required shaft power in kilowatts, rounded to 2 decimal places, so the key inputs and final result are easy to understand. This script estimates the hydraulic power a pump needs in kilowatts using flow rate, pressure rise, and efficiency. It validates that flow rate and pressure are not negative and that efficiency is between 0 and 1. The calculation multiplies flow rate by pressure rise, divides by efficiency, and converts watts to kilowatts. For the given inputs, the required power is about 1.75 kilowatts. Function scope. Function scope defines what a function is responsible for knowing, doing, and affecting. In engineering calculations, a well-scoped function should handle one focused task, such as a specific calculation, rather than an entire workflow. Keeping the scope narrow makes the function easier to test, reuse, and understand, especially by making its purpose and required inputs clear. When defining a function, keep its scope narrow and make required inputs explicit. Engineering calculations should not depend on hidden data or undocumented defaults, because assumptions about units and conditions can change the result. For example, a mass flow calculation should clearly use the needed physical parameters so others can verify that it matches the real situation. A function has effective scope when it can be reused in different engineering situations without major changes. It should have one clear responsibility, such as calculating a cylindrical tank's volume, and avoid unrelated tasks like printing reports or saving files. Keeping functions focused reduces side effects and helps engineers build larger programs from reliable, well-defined parts. Python code, function scope. This example shows focused function scope, where each function takes clear engineering parameters and returns calculated values instead of printing them. We define a tank volume function that takes a cylinder's radius and height in meters and returns its volume in cubic meters. Keeping this calculation inside a function makes the logic focused and reusable, so the volume can be computed whenever needed without repeating code. Before calculating the tank volume, the code verifies that both the radius and height are positive. If either value is 0 or negative, it raises an error. This prevents invalid dimensions from producing meaningless calculation results. The function calculates a cylinder's volume by multiplying pi by the radius squared and then by the height. It returns the resulting volume in cubic meters to the place where the function was called. The water mass function calculates water mass by using volume and density, with a default density of 1,000 kilograms per cubic meter. It first checks that both inputs are positive and raises an error if they are not. It then returns the mass in kilograms by multiplying volume by density, without printing any extra information. The code checks that the volume and density are both positive before continuing. Since 0 or negative values would be physically invalid here, an error is raised if either input fails the check. This prevents unrealistic data from being used in later calculations. The function finds the mass of water by multiplying the tank's volume by water density, giving a result in kilograms when the units match. It returns this value so other parts of the program can use it without printing anything itself. The cylindrical tank is defined with a radius of 1.2 meters and a height of 3.5 meters. These fixed inputs are used to calculate the tank's volume and the mass of water it can hold accurately. The process first uses the cylinder volume function to find the tank's volume from its radius and height. Then it uses that volume with the water density, typically 1,000 kilograms per cubic meter, to calculate the water's mass. Performing the steps in this order lets the functions be reused efficiently. The program prints a brief summary showing an example of focused engineering functions. It reports the tank volume to 2 decimal places and the water mass as a whole number, giving clear results in cubic meters and kilograms. It closes by emphasizing that the functions handle only their specific calculations, supporting a modular design. This script shows how modular functions can support an engineering calculation for a cylindrical water tank. One function checks that the tank dimensions are positive and calculates the cylinder's volume, while another uses that volume and a default water density to find the water's mass. Running the script displays both results, illustrating how focused functions keep each task separate and make the calculation easier to understand and maintain. Return values. Returning results. In engineering programming, functions should return results, so they provide useful data without controlling how it is used. A returned value can be stored, compared, or displayed in different parts of a program. This makes calculation functions, such as those for beam deflection or heat loss, more flexible, reusable, and easier to combine into larger workflows. Printing a value only displays it, while returning a value makes it available for later calculations. This matters in engineering because one result often feeds into the next, such as using a converted temperature or a pressure drop in another analysis. Returning results keeps functions reusable and useful for automated calculations and reporting. Returning a result makes a function clearer and more reusable. The function can focus on taking input, doing its task, and passing the result to other parts of the program. This keeps the core calculations separate from display, reporting, or user interaction, so those parts can change without altering the function itself. Python code, returning results. Focused calculation functions should return reusable engineering results rather than print them directly. Keeping printing outside these functions makes the results easier to test and use in later workflows. The beam stress function calculates axial stress in pascals from a force in newtons and an area in square meters. It returns the force divided by the area, making the calculation reusable, easy to test, and suitable for larger workflows. The function checks that the area is positive before continuing. If the area is 0 or negative, it raises an error, preventing invalid calculations, such as division by 0 or using physically meaningless values. The function calculates axial stress by dividing force by area, giving the result in pascals. Returning this value makes it available for later analysis or decision-making elsewhere in the program. The calculation starts by defining the key input values with clear engineering units: a force of 12,000 newtons and an area of 0.003 square meters. These values are then ready to be used to calculate stress accurately. The beam stress function takes the force in newtons and area in square meters to calculate stress in pascals. That stress is then converted to megapascals by dividing by 1 million, making it easier to compare with common engineering limits. An allowable stress of 5 megapascals is set as the safety limit for the design. The calculated stress is then compared with this limit, and the design passes if it is less than or equal to 5 megapascals. A passing result means the design is safe under the given conditions. The code reports the calculated stress and the allowable stress in megapascals using a clear 2 decimal place format. It then compares the two values and states whether the design passes the stress check. This shows whether the stress stays within the allowed limit for safe compliant design. This script computes axial stress by dividing a given force by a positive cross-sectional area, then reports the resulting megapascals. It compares the stress with an allowable limit of 5 megapascals and prints whether the beam design passes the check. Returning calculated results. A function that returns calculated results should focus on using its inputs to produce a value that other parts of a program can use. This is especially important in engineering workflows, where one calculation may feed into reports, estimates, or larger analyses. Keeping display and storage separate from the calculation makes the function cleaner, more reusable, and more reliable. Keeping calculations separate from presentation makes code easier to test, maintain, and reuse. A function that returns a numeric result can be checked directly against expected values without parsing the formatted message. This approach also keeps the function flexible for later uses, such as dashboards or optimization tools. Returning calculated results makes programs more structured and reusable. A function should take inputs, perform its calculation, and hand back a result that other parts of the program can use as needed. This reduces hidden dependencies, improves adaptability, and helps separate the work of computation from communication or interface design. Python code, returning calculated results. Calculation functions should focus on returning engineering results, not handling presentation. Keeping presentation separate makes the results easier to reuse in later workflows. The tank volume cubic meters function calculates the storage volume needed for a given flow rate and storage time. It takes the flow in cubic meters per hour and the number of storage hours, multiplies them, and returns the required tank volume in cubic meters for use elsewhere in the program. The calculation begins by setting two key inputs with clear engineering units: a design flow rate of 2.5 cubic meters per hour and a storage duration of 6 hours. Together, these values define how much flow must be stored over time and directly determine the required tank volume. The program calculates the required tank volume by using a volume calculation function with the design flow rate and storage duration as inputs. The result is stored for later use, so the program can apply it in further decisions. The selected tank has a capacity of 20 cubic meters. To find the unused space, subtract the required volume from this tank size. The result shows how much additional volume the tank can still hold beyond the project requirement. The output first shows the required tank volume from the earlier calculation, then the selected tank size, both in cubic meters. It also shows the remaining capacity, which is the difference between the selected size and the required volume. Together, these values make it easy to compare the needed volume, the chosen tank, and the unused space outside the calculation function. The script estimates the tank volume needed by multiplying a flow rate of 2.5 cubic meters per hour by 6 hours of storage, giving a requirement of 15 cubic meters. It then compares this with a selected tank size of 20 cubic meters and finds 5 cubic meters of remaining capacity. The output summarizes the required volume, chosen tank size, and unused capacity. Returning computed results. A function that returns a computed result produces a value other parts of a program can use. In engineering, this lets calculations such as stress or energy estimates be displayed, saved, or used in later work. Keeping the function focused on computation makes it easier to test, reuse, and adapt, while leaving presentation or reporting to other parts of the program. A common mistake in function design is combining the calculation with the message shown to the user. If a function only prints a result, that result is hard to reuse for other tasks, such as cost estimates or comparisons. A better design is for the function to return the computed value, while any display or report is handled separately. This keeps the core calculation flexible and reusable. Returning computed results makes calculations easier to test, verify, and reuse. It lets you check accuracy with known inputs while keeping the calculation separate from how the result is displayed. This separation makes software easier to maintain and adapt because reporting can change without changing the core logic. Python code, returning computed results. Focused calculation functions should return reusable engineering results, not handle output directly. Keep printing or display logic outside these functions, and use docstrings to record key assumptions, inputs, and units. The wall heat loss function calculates steady one-dimensional heat loss through a wall in watts. It uses the wall area, thickness, material thermal conductivity, and temperature difference across the wall to compute the result. This makes the heat loss calculation reusable in other analyses. The code first gathers the key inputs for the heat loss calculation: wall area, wall thickness, thermal conductivity, and temperature difference. Grouping these values makes it easier to check that each required input is present and valid before performing the calculation. The code validates that area, thickness, and conductivity are all positive before continuing. If any value is 0 or negative, it raises an error to prevent invalid or physically meaningless calculations. This calculation uses Fourier's law to find the heat transfer rate through a wall. It depends on the material's thermal conductivity, the wall area, the temperature difference across the wall, and the wall thickness. The result is the heat loss in watts, or the amount of heat conducted through the wall each second. The function returns the calculated heat loss in watts, so the value can be used elsewhere in the program. This keeps the function focused on calculation rather than output, making the code more flexible and reusable. This wall design example defines the key inputs for calculating heat loss: a wall area of 12 square meters, a thickness of 0.18 meters, and a material thermal conductivity of 0.045 watts per meter per Kelvin. The inside to outside temperature difference is set to 22 Kelvin, which is used to calculate heat loss through the wall. A heat loss function then uses the wall's area, thickness, conductivity, and this temperature difference to return the heat transfer rate in watts under the given conditions. To estimate seasonal energy use, first find the total heating hours by using 180 days at 24 hours per day. Then multiply the wall heat loss in watts by those hours and divide by 1,000 to convert watt-hours to kilowatt-hours. This gives the estimated energy consumed over the heating season. The output displays the calculated heat loss in watts and the estimated seasonal energy use in kilowatt-hours, both rounded to one decimal place for readability. It also clarifies that the function returns raw numerical results, leaving any formatted reporting to be handled separately. This script estimates heat loss through a wall using a one-dimensional conduction function. It uses the wall area, thickness, thermal conductivity, and indoor to outdoor temperature difference, and first checks that the inputs are physically valid. The function returns the heat loss in watts, which the script then uses to estimate seasonal energy use in kilowatt-hours. Documenting engineering functions. Docstring essentials. A docstring explains what an engineering function does, what it assumes, and how it should be used. It helps future users understand the function's intent without reading the code. For example, a pressure drop function should state the flow conditions and assumptions it relies on. This makes the code clearer and more dependable as an engineering tool. In engineering programming, clear docstrings are essential because calculations depend on units and conventions that may not be obvious from parameter names. They should state units for values such as temperature, length, force, and angle, and clarify conventions like sign direction or pressure type. This helps ensure results are accurate, meaningful, and safe for real-world engineering use. A good docstring should state the limits and assumptions behind a function so users know when its results are reliable. Engineering calculations often depend on simplified models, such as idealized beam behavior or battery use, so those conditions should be briefly documented. Clear docstrings make functions easier to test, reuse, and trust by preserving the engineering intent behind the calculation. Python code. Docstring essentials. Docstrings should clearly capture the engineering intent behind code, including important units and assumptions so the code is not misused. They should also make a clear distinction between what a function returns and any output it produces. The beam midspan deflection function calculates the midpoint deflection of a simply supported beam with a single central point load. It uses the applied load, beam span, modulus of elasticity, and moment of inertia, with inputs in standard engineering units, and returns the deflection in meters. The calculation assumes small deflections and linear elastic material behavior. The docstring states that the beam is simply supported and has one point load at its center. This defines the boundary conditions and loading case used for the deflection calculation. It also helps users understand when the function applies and what limits the model has. The function's documentation specifies the required input units such as newtons, meters, pascals, and meters to the fourth power. Stating these units helps keep the engineering calculations consistent and prevents mistakes from mismatched measurements. It also tells users how to enter values that match the model's assumptions. The function first checks that every input is positive, including the load, span, modulus, and inertia. This validation prevents invalid or nonsensical values from being used in the calculation, helping avoid incorrect results or runtime errors. The code verifies that all inputs are positive before continuing. If any value is not positive, it raises a value error, preventing invalid engineering inputs from being used in the calculations. The code computes a beam's midpoint deflection using the standard formula for the stated assumptions. It combines the applied load, span length, material modulus, and moment of inertia, producing a deflection value in meters. The function ends by returning the calculated deflection in meters. This gives the calling code the final result to use or display, while keeping the function flexible and reusable. The beam is described using 4 key properties: a 1200 Newton load, a 2.5 meter span between supports, a modulus of elasticity of 200 billion pascals, and a moment of inertia of 8.5 times 10 to the negative 6 meters to the fourth power. Together, these values define the applied force, beam length, material stiffness, and resistance to bending. The beam midspan deflection function uses the load, span, modulus, and moment of inertia to calculate how much the beam bends at its midpoint. The result is the deflection in meters, which helps evaluate the beam's response under the given loading and material conditions. The code converts the calculated deflection from meters to millimeters, which is more suitable for small values. It then formats the result to 3 decimal places for clear display, and adds a short reminder of the main assumptions, including units, loading, supports, and model limits. Together, these lines make the output easier to present in a lecture or report. The code prints a concise result showing the estimated deflection in millimeters to 3 decimal places. It also prints a brief reminder of the main assumptions, including units, loading type, support conditions, and model limits, so the result is understood in the right context. This script estimates the mid-span deflection of a simply supported beam with a central point load. It checks that the load, span, elasticity, and inertia inputs are positive, then uses small deflection theory to calculate the deflection. The result is shown in millimeters, along with a reminder to use consistent units and recognize the model's assumptions. Code comments. Code comments are most useful when they explain the engineering reasoning behind a calculation, not when they simply restate the code. They should capture key assumptions, such as material behavior or operating conditions, so future readers understand why a method was chosen. Good comments link the engineering model to the implementation, while keeping the code easy to follow. Use code comments to explain important engineering choices, not obvious operations. Focus on details that could cause confusion, such as unit conversions, safety factors based on company guidelines, boundary conditions, or limits on a calculation. Clear comments should highlight assumptions and decisions that future readers might question, while avoiding clutter that hides the critical reasoning. Comments help make engineering software maintainable by recording the assumptions and reasoning behind important choices inside a function. They are especially useful when code is reused in new settings, where limits such as fluid conditions or ignored heat transfer effects may no longer be valid. Comments do not replace docstrings, but they complement them by preserving context for future teams and revisited projects. Python code. Code comments. Engineering comments should clearly explain the modeling choices behind the work. Keep calculations separate from how results are displayed, and place units and assumptions close to the calculations they support. The function calculates the maximum bending stress in a rectangular beam and returns the value in megapascals. Before doing the calculation, it checks that the load, span, width, and height are all positive. If any input is 0 or negative, it raises an error to prevent invalid engineering results. For a simply supported beam with a central point load, the maximum bending moment is found by multiplying the load by the span and dividing by 4. Before calculating stress, the beam's width and height must be converted from millimeters to meters by dividing each by 1,000. To estimate bending stress in the beam, first find the section modulus by using the beam's width and height, with the height squared and the result divided by 6. Then divide the maximum bending moment by this section modulus to get the stress in pascals. Finally, convert pascals to megapascals by dividing by 1,000,000, which makes the result easier to compare with engineering limits. The function returns the calculated stress in megapascals, making the result available for reuse elsewhere. This keeps the calculation modular and flexible, so it can support larger programs or further analysis without rewriting the same logic. The beam setup defines a 1,200 Newton load, a 1.8 meter span between supports, and a rectangular cross-section that is 40 millimeters wide and 80 millimeters high. These dimensions provide the needed inputs for calculating beam stress later. A beam stress function is used to estimate the maximum bending stress in a rectangular beam from the load, span, width, and height. It returns the stress in megapascals, which can then be saved and checked against acceptable limits. Set the allowable stress limit to 150 megapascals. Then compare the beam's calculated stress against that limit. If the stress is at or below the limit, the design is acceptable. Otherwise, the stress is too high. The output reports the estimated stress to one decimal place, the design limit, and the resulting status. This script estimates the maximum bending stress in a rectangular beam with a central point load. It uses the load, span, width, and height, checks that the inputs are positive, converts dimensions as needed, and calculates stress in megapascals. The result is compared with a 150 megapascal design limit, then reported as either acceptable or too high for safe use. Expected inputs. When documenting an engineering function, clearly state the expected inputs so users know what data the function needs to work correctly. A good docstring explains what each input means, its required units, and its format, such as meters, Kelvin, or numeric material properties. This makes the function easier to reuse, test, and apply correctly in different workflows. Clear documentation of expected inputs helps prevent silent errors that produce wrong results without crashing a program. Engineering functions should state required units, valid ranges, and assumptions, such as positive lengths and consistent unit systems. This makes valid use clear and helps users catch edge cases like zero or negative values, missing data, or conditions beyond the model's scope. Document a function's expected inputs briefly but clearly, so others can use it without reading the code. State what the inputs represent, such as measured values, design specifications, or empirical data, and note key assumptions like ideal or steady-state conditions. Add comments for non-obvious choices, including range checks or default values, so the function remains reliable and understandable in future analysis. Python code. Expected inputs. Engineering functions should clearly state what inputs they expect. Docstrings document key assumptions and required units, while validation helps catch common input errors early. This function estimates the heat energy needed when a fluid's temperature changes. It takes the fluid's mass, its specific heat capacity, and the temperature change, then multiplies these values to return the energy in kilojoules. The inputs are assumed to be physically meaningful, with positive mass and specific heat, and a non-negative temperature change. This heat energy function takes mass, specific heat capacity, and temperature change as inputs. To be valid, mass and specific heat capacity must be greater than zero, and temperature change must not be negative. The function first checks that the mass is positive and raises an error if it is zero or negative, preventing calculations with physically invalid values. The code first checks that the specific heat capacity is positive before doing any calculations. If the value is zero or negative, it raises an error to signal invalid input. This helps prevent later calculation problems by ensuring the input is within the expected range. The code rejects any negative temperature change by raising a value error. This enforces the assumption that the temperature change must be zero or positive in this context. This calculation finds the heat energy needed by combining the fluid's mass, specific heat capacity, and temperature change. It returns the energy in kilojoules and assumes the specific heat is constant, with no phase change. To calculate the heat energy needed, we use three inputs: a water mass of 2.5 kilograms, water specific heat capacity of 4.186 kilojoules per kilogram per Kelvin, and a temperature increase of 18 Kelvin. Together, these values describe how much water is being heated, how much energy it takes to warm it, and the size of the temperature change. A heat energy function calculates the energy needed to warm water. It uses the water's mass, the specific heat capacity, and the temperature rise as inputs. Then it returns the total required energy in kilojoules. The heat energy in kilojoules function prints its name, the required input units, and the key assumptions: no phase change and constant specific heat. It then reports the calculated energy needed, rounded to 2 decimal places and expressed in kilojoules, so the result is clear and easy to interpret. This script estimates the heat energy needed to raise a fluid's temperature using its mass, specific heat capacity, and temperature change. It first checks that the mass and specific heat are positive and that the temperature change is not negative, then reports an error if any value is invalid. In the example, it calculates the energy required to heat 2.5 kilograms of water by 18 Kelvin and prints the result in kilojoules, rounded to 2 decimal places. The method highlights the importance of valid inputs and assumptions such as constant specific heat and no phase change. In this lecture, you learn to define functions that perform focused engineering calculations with clear parameters, return calculated results without mixing computation and user-facing output unnecessarily, and document assumptions, units, and expected inputs using concise docstrings and comments. In the next lecture, Lecture B, we will go over files and errors. Thank you for your attention. See you all in the next lecture.